Hi, welcome to today's video. This is going to be a reasonably short one, but we're just going to be looking at ionic equations. Now, an ionic equation is an equation involving ions. Now, no, that's not it. It's not that short, this video, but I want to show you why we sometimes use ionic equations in chemistry. So I'm going to start off by just looking at two reactions, okay? So first I'm going to start off with is looking at taking some sodium chloride, NaCl, which is soluble in water. So we give it the term AQ, okay? And I'm going to react that with some silver nitrate, AgNO3, which is also soluble in water, okay? So both of those are given their symbol AQ. Now, when they react, okay, you put them into water. So this is a clear solution, this is a clear solution, okay, clear and colorless, both of them. When we put them in together, we get this white precipitate forming. Now that white precipitate is silver chloride, okay, so that's actually a solid, that's insoluble in water, and we also get sodium nitrate, okay? So nothing really groundbreaking about that equation. What I'm going to do now is I'm going to show you a second equation that we're looking at here. And so I'm going to just set them up a little bit different because I want to show you what I'm talking about with this one. So the second one we're looking at is I'm going to take, so this time, some silver fluoride, which is soluble in water, so that's aqueous. And we're going to react that with some zinc chloride, which is also soluble in water. And when we react these together, we get this. Again, what we get is some silver chloride solution. Sorry, this blue one's dying. All right, silver chloride, which is actually a solid in solution. And we get some zinc fluoride, ZnF2. So we obviously need to balance this up with a 2 there and a 2 there. Now, if you're having a look closely at these two reactions, you'll see that if you were putting these together, you'd pretty much see exactly the same thing. You'd have clear colorless solutions, but when you add together, you get a milky white solution. You have two clear colorless solutions, and when you add them together, you get a milky white solution. And the reason for that, I should point out, sorry, that this is aqueous, so that's soluble in water, and the sodium nitrate is also soluble in water. So for both of these, what they have in common is this silver chloride precipitate that's being formed. So it doesn't actually matter which of these two reactions we do, the observation we would see would be the same, where we get a milky white precipitate in there, which is due to the silver chloride. So we can show that with what's called ionic equation. So let me rub this out and I'll show you. So both of those reactions can actually be simplified down to just this. A silver ion, Ag+, which is aqueous, reacting with a chlorine ion, which is also aqueous, gives us solid silver chloride. So this is an ionic equation because what we're doing is we're showing just the reaction involving the ions that forms a precipitate. So precipitation reactions we sometimes write as ionic equations because we don't actually really care about what else is involved in the reaction. So those other things that were in there, we had some sodium ions, nitrate ions, we had fluorine ions, we had zinc ions. Doesn't really matter about those ones because they both ended up with this same precipitation reaction occurring. So those other ions, which we aren't showing in the equation here, we call spectator ions. Spectator ions, and again, I'm sorry, these pens are really squeaky today. Spectator ions are ones that are involved in the reaction, but they're not directly involved in either the precipitation or what we're really interested in. So it doesn't really matter what they are. So we leave spectator ions out of ionic equations. So precipitation reactions is one where we use ionic equations. The other place that we really use ionic equations is in acid-base reactions, because we know that acids are proton donors and bases are proton acceptors. So in reality, what's really happening with most acid-base reactions is that you've got your acid, which is H+, and then it's reacting with a base. Okay, now that could be the hydroxide or it could be anything else, doesn't matter, and to give us salt plus water normally. Okay, So what we're doing in here is we're getting our anion from the salt. So we're getting the salt anion plus we're getting water. Okay, so because it doesn't really matter what the spectator ion is for the acid we're using. So if we're using hydrochloric acid, or if we're using nitric acid, or if we're using sulfuric acid, or even if we're using acetic acid, and I'm just going to write it this way, the main thing that we're concerned about that all of them have in common is that this H plus here, the hydrogen, is what's involved in the reaction. That's the part that gets donated. It doesn't really matter what the other parts are, okay? Now, sorry, up here I've actually written salt anion. That should be salt cation, sorry, because the anion part here is being left off. So I'll just adjust that for you shortly, and I'll show you what I mean with an equation. So that's going to be the salt cation. I think the problem is my brain's not functioning because I haven't had enough good Farmers Union iced coffee goodness. So we can write ionic equations for acids using H+, and that's often the case. So you might just see a question, something like, write an equation for calcium carbonate reacting with an acid. Now you don't know what acid it is, but it doesn't actually matter because that equation, and I'll swap colors for you here. I'll go to this one. Okay, so that equation would be any acid is a H+, reacting with the calcium carbonate, CaCO3, okay? What we're going to get here, and again, this is a slightly different sort of reaction from what I've shown up here, sorry, but we're going to get the salt cation. So the salt cation is going to be Ca2+, okay? And then, so it doesn't matter if it's chloride, nitrate, sulfate, or the acetate here, that would just be combining onto here to make our salt. And in this case here, an acid carbonate reaction would give us carbon dioxide and water as well. So we can use ionic equations to show acid-base reactions as well. Now, the important thing about ionic equations is they still follow all the same rules of normal equations. So all your atoms must be balanced. But also what ionic equations also do is they also balance up the charge. So you see we've got 2 hydrogens here on the left-hand side for the reactants, and so that's 2+, and we've got a 2+ on the right-hand side from the calcium. So the charges also balance. So we're not changing anything out. All we're doing is removing those spectator ions, which are those ones that aren't involved in the reaction because they don't really matter, okay? So hopefully this has been fairly straightforward for you. As always, if you've got any questions, just ask. Have a good day. Thanks, guys.